Hello, I am Dr. Stephen Wheat with QCT's HPC Business Unit. I am going to talk about QCT's path to hybrid HPC and AI systems. The motivation for this talk is based upon the continued significant annualized growth rate of traditional HPC use cases, while at the same time, new AI-based use cases continue to emerge and proliferate, and the two spaces, HPC and AI, continue to increase their intersection. It is becoming increasingly common that an HPC site would be installing AI capabilities, and at the same time, it is true for sites that were doing AI, for example, business intelligence, are now adding HPC methods to their workflows. The observation is true for every vertical. In manufacturing, it is quite evident in the advanced development of quality inspection, and it is foundational to the Industry 4.0 movement. In life sciences, we see it in image recognition, enhanced diagnostics, and drug discovery through AI. In the seismic community, we see it being applied to interpret seismic surveys in new ways. Last year, we focused our message on the transition from an application focus to a workflow focus, where workflow involves potentially many applications being applied simultaneously and over time, all needing resources. Then we spoke about organizing the building blocks in a manner to support the workflow and having the building blocks configurable to different workflows without introducing one-off products. A key reason for this is that it must be recognized that performance opportunities and bottlenecks wax and wane throughout the workflow. On the next slide, we will gain some insight into what this can mean. But here, we kind of review that we have a horizontal approach supporting infrastructure, going left to right, providing compute capabilities, storage capabilities, network capabilities. We have a level of resource provisioning, left to right, based upon whether we're doing bare metal or cloud-based provisioning. And then we have resource management on top of that, to where these systems have a systematic and consistent manner of management. It is generally recognized that GPUs have unleashed a new level of capability for artificial intelligence, machine learning, deep learning workflows. But a strong foundation for bringing them into fruition started with accelerating traditional HPC codes. With the continued dedication and fortitude of the development community, the rate of porting applications to utilize GPUs has continued unabated. This has happened across most HPC application domains such as physics, bioscience, molecular dynamics, chemistry, and weather forecasting. Between the AI and HPC workloads, demand for GPU nodes is increasingly more common, even for smaller HPC systems. But it is still not the case that every node would be accelerated. We're not there yet. So optimizing the system design for the appropriate population of GPUs is key. That's what the next slide is going to help us understand a bit more about how systems need to have a balance across several metrics. Here we have a visual from IBM Research. This maps applications into the following three dimensions: compute versus data centricity, the vertical dimension in the drawing, with compute-centric being down and data-centric being up. Computational type, floating point operations versus integer operations, that's on the left to right dimension. The degree of spatial locality of data on the fore to aft dimension, with the high spatial locality being to the fore. A given application will ebb and flow in each of these three dimensions. To achieve an optimal system solution, one would map all the applications over time and determine the scale of each capability to build into the solution, such that the cube of the solution space would envelop the whole workflow over time. This perspective will drive the necessary capacity for each type of system building block for an optimal price-performance solution design. And of course, we're focused on a hybrid system where we would have GPU and CPU jobs all having to fit into that cube optimally. An integrated hybrid system is one where compute nodes would include both CPU nodes and GPU nodes. We contrast this to having two different systems, distinct systems, one with CPU nodes and one with GPU nodes. While a hybrid system is more complex, it can bring much more benefits because it's more flexible, it's efficient in the use of common equipment, common building blocks, and its cost effectiveness because of that. QCT recognizes that complexity that we spoke about in the prior slide. We observe that there are a few existing pain points in the market for three kinds of roles, respectively: administrators, developers, and users, where, first, administrators need to be aware when something goes wrong. They have to know what would need to be fixed and recovered. Second, developers usually need to spend lots of time building the development environment by themselves. It is better for them to get all the software tools and switch between different versions of kernel for testing. Third, end users might not be familiar with HPC infrastructure and the runtime environment. QCT offers several benefits for each of these roles. The QCT software stack allows administrators to manage and monitor clusters easily. Processes can be streamlined and integrated with different administration workflows. For instance, they can use the graphic user interface dashboard to monitor the system. As for developers, they will benefit from easy-to-use software tools that include module files and provide predefined compilers and math library configurations. Also, if they want to change one environment variable, they can leverage module files without logging in and logging out and the complexities thereof. Lastly, end users will benefit from templates and industrial workload packages, where they can leverage QCT's JavaScript templates to prepare their runtime environment. QCT also provides tools such as preloaded viewers to support visualization. With respect to designing a hybrid HPC AI solution, we apply QCT's three key value propositions. First, in the beginning, when a customer wants to implement an HPC AI system solution, QCT will partner with them to understand their design needs and choose the most suitable architecture and carry out a selection of infrastructure from QCT's broad portfolio of products. Our clients can also scale out the infrastructure architecture on demand based upon QCT's modularized architecture design. Secondly, QCT can reduce customers' efforts and time on integrating and deploying a system because QCT offers rapid deployment service that integrates the software stack, the parallel file system configuration and tuning, and the applications before delivery. Finally, QCT's solution can speed customers' time to value. QCT precompiles the environment variables for different industrial applications to accelerate our customer success. Further, we provide comprehensive software tools for users to simplify their daily workflow. As mentioned earlier, QCT has a broad portfolio of HPC and AI products to fulfill different use cases. Here are the system architecture and server modules we designed. For compute nodes, we offer a 1U 1-node server for general computing, 2U 4-nodes server for high density, an 8 GPU double wide capable of doing NVIDIA A100 GPUs PCI, that all in a server for GPU acceleration and deep learning and machine learning. And a 3U 4 GPU server is a cost-effective option supporting NV Bridge as well. All these models support AEP memory and NVMe drives. For utility nodes, we offer CPU servers for general purpose. but stay flexible to offer GPU servers if the customer needs graphic acceleration as well. For the high-speed fabric, we offer Mellanox, NVIDIA, Infiniband, and QCT Ethernet infrastructure. For storage nodes, we offer a 1U, 1-node solution. We offer a 2U, 1-node solution for parallel file systems and storage servers, as well as QCT's JBODs, the JB4242 and the JB4602. We compose 2 servers with 1 JBOD as a set to build a storage pool. QCT leverages the open HPC community software stack for users to deploy a general-purpose HPC cluster. On top of that, QCT has added more functionality and features. In terms of system architecture, we separate login node and head node to become user and administrative portals as compared to the default of the open HPC recipe. We also added a GUI dashboard monitoring environment, system management tools, multiple options of parallel file systems, and a machine learning framework and platform. Applications we'll cover on the next page. To support scalable system administration, QCT leverages centralized user authentication, such as NIS, LDAP server, to offer a location for administrators to manage user account information in a scalable manner. QCT has the tools and products to optimally deploy HPC AI hybrid systems with high availability and load balancing environments as well. To quickly adjust to a hybrid system, users can leverage QCT pod solutions, which include multiple options for system deployment and system management and monitoring. QCT pod is QCT Platform on Demand. All users and developers can interactively access and use pre-installed and pre-configured development tools such as data visualization viewers and MPI and deep learning application frameworks to run their workloads on computing building blocks, storage building blocks via the web user interface, such as Jupyter Lab. The command line interface and the remote graphics desktop service such as X2GO and VNC, which are serviced by the management building blocks. Take some time to look over this. You'll see what we're talking about with respect to system deployment, how we go about that, system management and control, user interfaces, the development environment, our pre-configured workloads, for example, in molecular dynamics, climate and weather, quantum chemistry, next generation sequencing, and of course there are the application frameworks for deep learning, the MPI environment, of which we have all the flavors of MPI, and of course the popular versions of containers. Let's take a look at a real-world example where we are going to actually be taking an existing system and adding to it a hybrid solution. So it's a hybrid of hybrids. On the right-hand side of this, we plan to build a hybrid system that includes CPU, GPU, and big memory nodes. On the left-hand side, we have a pre-existing AI system to which we'll integrate the right-hand system to it. This integration will include the Ethernet, different generations of InfiniBand, EDR, and then HDR, all coming together, the development environment, and the user management. Also, we will need to leverage the parallel file system in the previous AI system. Let's take a deeper look at how we will go about doing this. In this project, QCT will first build a new hybrid CPU, GPU, HPC system. This includes securing all the interconnects between nodes for quick system deployment, building the first deployment node, deploying the OS to all the utility CPU and GPU nodes, and optimizing the operating system after the deployment stepwise. Then we will integrate with the HDR InfiniBand network the pre-existing EDR network. This will include upgrading the EDR network components, including the drivers and firmware for both the switches and the host base adapters. After the network integration is completed, then we can share the original parallel file system to the new hybrid HPC system, well, throughout the whole system. Then we will perform integration and benchmark tests to ensure that performance of all the components meet our expectations. We will see more details of this as we get into the fabric details that are involved here, as well as how we actually do the benchmark with a heavy-duty application. And now let's take a closer look at the Infiniband Fabrics. Let's start from the original EDR fabric of the AI system, the pre-existing system. The original design was to use a core spine leaf 3-tier architecture to reduce the number of Infiniband switches needed, and also ensure that performance would be sufficient. It was divided into 9 small GPU groups of 18 GPU nodes each, 9 groups of 18 GPU nodes, and 3 large GPU groups with 30 nodes each. Each of these 12 groups is a non-blocking fabric within themselves. For each of the small and large groups, we used 1 to 3 oversubscription to go to the next link up. We have found that that was indeed able to satisfy the performance requirements, including to the utility nodes. As for the utility group, which consists of 80 nodes that handle the parallel file system, we use a 1-to-1 non-blocking ratio to the uplink switches to ensure all the data can be read or written to the file system without bottlenecks. What we see again is 9 small GPU node groups, each with 18 nodes. Now, in this particular case, each one of those nodes has 4 InfiniBand links. 4 by 18 is 72. Same goes for the 3 large GPU node groups. We have 30 nodes in each of those groups. Each node has 4 InfiniBand connections, and hence the 120 InfiniBand links coming in there. The utility group with 80 nodes, with 1 link each, 80 InfiniBand links. All the nodes in the same group are connected with spine leaf architecture in a non-blocking manner, as I mentioned earlier. And in the new hybrid HP system, we design a spine leaf 2-tier architecture for the new system. We used a 1-to-1 non-blocking ratio in our design for the connections between the spines of the pre-existing EDR fabric and the new HDR fabric. We will also take advantage of NVIDIA's split cable design that will split one HDR 200 port into 2 HDR 100 connections to increase the total number of nodes that can connect to that switch, and to ensure the maximum bandwidth and least blocking within the CPU and GPU nodes. So here, all CPU and utility nodes in the NIC system are connected with HDR IV fabric. 2 nodes are connected to 1 port of each of the HDR switch ports, and then we have a 24-leaf InfiniBand HDR switches are connected to 20 spine InfiniBand HDR switches in a non-blocking manner. And these 20 spine IB HDR switches are connected to 24 core EDR switches in the original system via 120 EDR links. In the prior slide, we talked about all these different connections into the Infiniband fabrics, so the HDR fabric, the EDR fabric connecting to the HDR fabric. It can be relatively complex. It's not something you want to do by hand, so tools help. We can check our fabric topology through NVIDIA Mellanox's Unified Fabric Manager. This UFM tool provides a powerful platform for provisioning, monitoring, and operating the Infiniband fabric. We can now see the topology here of the original EDR fabric. See the 9 small groups in green circles and 3 large groups in blue circles connecting to the upper spine switches, and then connecting to the new HDR fabrics in the red circles. UFM also serves as a useful monitoring tool, which will allow us to check the bandwidth usage and find suspicious ports and cables that would otherwise be detrimental to the fabric performance. And without the tool, very hard to find why performance is not meeting our expectations. So definitely, tools pre-integrated to support doing something like this is part of QCT's solution designs. So we can build the hybrid system of hybrid systems, and we can test it individual components. We can use UFM to be able to look at fabric performance, make sure everything is working individually well. But when it comes to actually working at scale, we need to start doing some application testing. So we chose to use the Vasp code to do that. Vasp, the Vienna ab initio simulation package, is one of the most widely used models for electronic structure and first principle molecular dynamic simulation. We used the lead silicon 111 case for the benchmark. To prepare for the full-scale benchmark, we ran the benchmark over 4 QCT D52G GPU nodes, each with dual 8280 Xeon CPUs and 8 NVIDIA V100 GPUs. There we measured the performance of Vasp on CPU only and on both CPU and GPU of varying different scales. This slide we'll spend some time on. This slide shows the performance of Vasp normalized on a single node. That node, this node here, establishes our baseline. On 2 nodes, we see that Vasp is running at not quite 2 times faster, but 1.8. That's not too bad, 1.8 times faster. But on 4 nodes, we're seeing it start to fall off on the scalability. Now, of interest, let's go back up to our 1 node situation. If we add 1 GPU to that, we find that we will get the performance of improvement of 40%. And if we add 2 GPUs to that, we get 2.6 right here. So that's roughly 1 node plus 2 GPUs. That's roughly the same performance of 4 CPU nodes by themselves. 2.4 versus 2.6 up here. And so what that will do for us is we're starting to see some improvement of 1 node, 2 GPUs. Now let's take it to 4 GPUs. Now all of a sudden we're at 5 times. Okay, so 1 node with 4 GPUs is 5 times the performance. And what's interesting is we're getting some substantial scalability as we go to 8 GPUs, which we can do in that same chassis. And we end up with a 9.1 factor over that 1 node. So we get the original node's worth, plus for every GPU, another node's worth of performance. And so that's an interesting type situation going across here. So left to right, we see 1.4, 2.6, 5.0, and up to 9.1. Various interesting things that we can get into as to why the scalability works that way. But you can imagine more and more the GPU, the workload is fitting into the GPU memory, et cetera, et cetera. So what about 2 nodes? Well, 2 nodes with 2 GPUs each, or total, I should say, sorry, 2 GPUs total, gives us a 2.5. Well, that's kind of the same as what we have with 4 nodes without, or 1 node with 2 GPUs. So 2 GPUs total, yeah, we're pretty much getting the same performance right here. Similar kind of situation, when we go to 4 GPUs total, in this case it's 2 GPUs per node, we're falling off a little bit, and that's because we're going across the fabric between 2 nodes. 8 GPUs total, 4 per server. We get this 6.4 instead of the 9.1 with all 8 GPUs inside of a single node. So we're seeing some scalability limits because of the having to use the fabric instead of using the PCI environment to communicate between the GPUs. And of course, with 2 nodes with 8 GPUs each, we can run that and we're getting 7.5. What is this telling us? We're starting to fall off pretty quickly on the performance. If we're really kind of focusing on this particular code and it's a major portion of our workflow, we're kind of focusing in on, perhaps this 8 GPU node. But again, Vasp is a workload itself, and there could be other workloads on the system. We might find that that cube that we talked about may need to comprehend other applications, of which the 4 GPU per node may be actually the optimal solution as we start dialing in the dials. And we'll see that it's not a bad situation for Vasp. If we had 2 nodes, 4 GPUs, we ran 2 Vasp jobs, great, we could do that. And maybe what we end up doing is a handful of the nodes have 4 GPUs and a few have 8 GPUs. So this is telling us the sweet spots around how we could mix and match different GPU configurations for this workload, and we can do the same kind of thing for other workloads to get to an optimal solution for an end customer's perspective. So what we're seeing is this mapping helps us to really understand optimal system design, as well as gives us a tool by which we can now, with this performance, we can go and actually test the nodes at scale and make sure that at scale all the nodes are running, so we can launch a bunch of Vasp jobs across it and verify that the system is behaving as we would expect it to do so. In summary, we have seen that hybrid systems are going to be the way to go move forward with. We're just seeing AI increasing in the HPC space, and we're seeing HPC increasing in the traditional AI space. So that overlap, that intersection of the two is just growing. Small system sites, large system sites are all grappling with how to do this. We have a position that a hybrid system that is built upon common building blocks, a common framework is the way to go with this. So GPU accelerated computing will greatly boost the performance of codes that have traditionally been only done with CPUs. And we saw that in the slide that was showing that we have this progression of more and more codes year after year being ported to the GPUs. So it's no longer that kind of a niche-like situation. It's a substantial amount of the codes. So most of our customers' codes are going to be able to be touched by GPUs. Now, if they're not, then some of their codes may be, and their AI workloads, we can still work out that cube of the workflows that they have in order to blend the system together in a hybrid environment. And that hybrid environment lets us do more with less by being able to capitalize on those common building blocks between the two systems when we actually put them together. And of course, with us looking at this at the system level, at the design of our building blocks, how we connect those building blocks together, the value of the QCT solution is that we're going to shorten that implementation activity to get to a system design, deployed, and operational by the end user. And so the whole point is to be able to adopt the technology quickly, and there's a value to that as well. The technology ages, and the longer it takes to be able to deploy something, the less value it is over its lifetime that you have. And so we do want to make sure we accelerate and take the greatest of the value of the technology at its earliest part of its lifespan. And so bringing greater value to the customer. I hope you have enjoyed this conversation about the hybrid solution, gained insight into QCT's approach to it, the QCT breadth of portfolio, not just of the building blocks, but also the software stack, as well as the system solutions, QCT platform on demand solutions to even get it closer to a turnkey situation for an end user. Thank you very much. And again, I'm Dr. Stephen Wheat with QCT's HPC Business Unit. Have a good day.